This is Sean Harris, and today we're going to go through hashing, message authentication codes, and we're also going to quickly look at digital signatures and what the services that are provided by these cryptography approaches. So there's a whole algorithm set that is responsible for providing integrity, and these are hashing algorithms. Digital signatures that we look at will provide integrity, non-repudiation, and authenticity. We'll also look at message authentication code. There's two types of method authentication codes we need to understand, HMAC and CBC-MAC. And these message authentication codes actually provide different security services than using just hashing algorithms or digital signatures, which we need to understand for the exam. Now, many times when people think of cryptography, it's just about confidentiality. What's commonly thought about is encryption and decryption, which does provide confidentiality. But as I said, there's a whole different set of algorithms used just for integrity, and that's what we're mainly going to look at today. So here we see an example of some of the hashing algorithms that you need to be aware of, and you'll need to know the specifics of these algorithms. And their outputs we see as message digest values, which we'll go through how those are created. So a hashing algorithm will take a variable length string and generate a fixed length value. That's kind of a complex way of saying that a hashing algorithm will just take a message of any size. So you could write a message of 2 lines or 3 pages. And the hashing algorithm will take that's variable length string, and will generate a fixed length value. Each of the hashing algorithms creates a specific size of message digest value or hashing value. Message digest algorithms create 128, which we'll look at. SHA, which is secure hashing algorithm, creates 160 bits. So that's what it means by fixed length value. Sometimes people understand the concepts of hashing, but this specific definition can be a little confusing. So there's no key involved with hashing. With encryption and decryption, we do have a key that provides randomness to the algorithm that's used, but confidentiality is not one of the services provided by hashing algorithms. And one of the main reasons is there's no key involved, but also this is just a different algorithm type that does not provide encryption and decryption. If you're familiar with a CRC function, this is similar to what a hashing algorithm does. The CRC function will look for any type of message integrity issues. For example, if I send you a message and I have maybe a CRC fingerprint attached to it and I send it over to you, your system is going to do the same CRC function and create a fingerprint of that message and compare them to see if there's been any type of modification during transmission. Now, CRC functions work at usually about the data link layer of the OSI model of the network stack. So CRC functions are more about network transmission corruption, where hashing is looking at the data payload of an actual packet. So a hashing algorithm is looking more at when people actually change a message on purpose versus if there's a transmission error. So any change to the data payload, as we see here, means that the output, the fingerprint from the hashing algorithm, should change. And if it doesn't change, this is referred to as a collision, and that means that there's a weakness within the hashing algorithm itself. So we see the input into the same hashing algorithm, and as the input actually changes, the message digest value changes. Now, the result of a hashing algorithm can be called message digest value, hashing value, or a fingerprint. And you do need to know those 3 different labels. They all refer to the same thing, but in the exam you could see one or more of those labels. So let's walk through how this would take place. I'm going to send you a message, and I want to make sure that message has not been modified while in transmission, and for you to get the exact message that I send. So I'm going to be repetitive on the hashing methods. We're going to look at the message authentication code approaches and the digital signature methods. So we're going to see some of the same concepts in the different slides, mainly because cryptography and these integrity approaches are new to some people, and it's important that you understand the foundations before we build upon them. So if I'm going to send you a message and I want to make sure that you receive the same message that I send you so there's no integrity problems, I'm going to put my message through a hash algorithm. And as we saw, there's different sets of algorithms or different types of hashing algorithms, and we'll look at some specific examples in a few minutes. So I take that message and I put it through a hash algorithm. From there, I get a message digest value. Remember that a message digest value can be called a hashing value or a fingerprint. So my message, after putting through a hashing algorithm, what I get out of that is a message digest value. I attach that message digest value to the message I'm going to send over to you. Now, I'm not using a key. This is not encryption. There is no confidentiality provided. This is purely integrity. So you receive my message. You take the message digest value that I have attached to the message and you run it through the same hashing algorithm. You come up with your own independent message digest value and you compare the two. If the two are the same, the two message digest values that I created and that you created are the same, then you have the confidence that the message has not been modified before it got to you. So let's step through this conceptually. A message is created. Let's say you create a message to me. You create a message, you put it through a hash algorithm. You see that a message digest value is created. You attach the message digest value to the message that's going to go over to me. Now see that this message has not been encrypted. It has only gone through a hash algorithm. Hashing algorithms do not encrypt data. So the message and the digest value goes over to me. I take the same message, I run it through the same hashing algorithm, and I come up with my own independent message digest value. You see that your message digest value does not have a number. Mine has a message digest value number 2 because it's independently created. So as I said, if the hashing values do not equal each other, so you receive my message digest value with my message and the hashing algorithm creates a different message digest value that is not the same as what I sent over, then your system is just going to discard this message. And when I say that you or I are going to write a message, we put it through a hashing algorithm, this all takes place in the background, thank goodness. It takes place in the background by our software, by our crypto system. We as users can choose to do the configuration of choosing hashing or message authentication code or digital signatures. And it is important, everything I'm talking about is important for the CISSP exam. And I'm just going to say this again, is that this type of integrity checks are at the higher level of the network stack. Any type of transmission errors usually take place at the bottom of the network stack. And what we mean at the bottom of the network stack, we're looking at actual headers within a frame. When we're looking at integrity issues with hashing algorithms, we're looking at the higher portion of the network stack, which is the data payload of the packet itself. So here are some examples of hashing algorithms you do need to know for the exam. You need to know some more specifics about each algorithm than what I'm showing here. But one thing you definitely need to know is these are hashing algorithms, and you need to know the size of the message digest values they create. So the whole family of message digest hashing algorithms creates a 128-bit digest. And remember, the definition is that a hashing algorithm can take a variable size message, meaning your message could be of any size. When you run it through a hashing algorithm, if it's one of the MDs within the MD family here, it's always going to create a 128-bit digest. So the variable length string is your message. The fixed length result is the message digest value. You'll need to know why there's message digest 2, 4, and 5. Of course, they're getting stronger over time. You'll need to know a little bit more information about that. You shouldn't see anything about SHA, secure hashing algorithm itself, without a number behind it, because SHA was it's become obsolete. There's been some problems found in it. So SHA-1 is stronger than just SHA. And when you see SHA and then a number like 512, 128, that number at the back of it, SHA-512, that means it's going to create a message digest value of 512. So here's just an example where a user can choose which hashing algorithm that's going to be used. And you also see a CRC function that will be chosen, which again has to do with more of the transmission errors. In the last Video Mentor presentations, we looked at symmetric and asymmetric algorithms. Here we have AES, which is a symmetric algorithm, and we have RSA, which is an asymmetric algorithm, and we have a hashing algorithm, SHA-1. Now, if I send you a message, so let's say I write a message, I put it through the hashing algorithm, I come up with that message digest value. I send you the message with the attached message digest value. Now, when you create your own message digest value and compare the two, how do you really know that that message has not been modified? If I write you a message, I create the message digest value, I send you over the message, how do you not know that that has not been modified? Because what's going to happen is, no matter what message you receive, your system is going to put that message through a hashing algorithm and come up with your own independent message digest value. And there are collision attacks or birthday attacks that can make cause collision, which means that both message digest values are the same. So a lot of times we need to have more protection for integrity of our data going back and forth than just using hashing algorithms. So let's look at how these types of attacks would take place. So we have Bob at the top and we have Alice at the top on the right hand side, and below is Dave. So Bob and Alice are communicating, and Bob writes a message to Alice. He puts the message through a hashing algorithm and he comes up with a message digest value. So he writes Alice a message, attaches the message digest value, and it goes over to Alice. Now, Bob and Alice think they're communicating just back and forth. They don't realize there's a man in the middle. So Dave can take the message that Bob has sent over and he can modify it and he can calculate a new message digest value and send it over to Alice. She's going to take the message that Dave wrote, calculate her own message digest value, and they're going to be the same. Alice's message digest value will be the same as the message that Dave sent over, but Alice thinks that message came from Bob. So let's walk through this one more time. Bob sends Alice a message. He runs the message through a hashing algorithm and creates his own message digest value. He sends the message over to Alice, but Dave grabs it. He grabs it before it gets to Alice. Dave will change that message and create a new message digest value and send the message and the new message digest value over to Alice, she will take that message that she thinks is from Bob and run it through a hashing algorithm and come up with her own message digest value and compare the two. Since they match, she thinks that what Bob sent over is exactly the message that he wrote, which is not, because Dave has modified it. So the sender and receiver think they're communicating just to each other, and this is another example where Tanya and Erica think that they're communicating with each other, but all of their messages are going through Lance. So if Tanya writes Erica a message, Lance could read it, modify it, send it to Erica. Erica can reply with a message. Lance will grab it, can either read it or modify it and send it over to Tanya. If we're using just hashing, this could take place. So if we do need more protection, then we're going to implement message authentication code. This is basically using a hashing algorithm and using symmetric cryptography. We're going to be using symmetric keys. So there's two types of MAC. MAC is message authentication code. We're going to look at hash MAC and CBC MAC. Now these both provide what's called the weakest form of authentication. If we need a strong form of authentication, then we're going to use public key cryptography. We're going to use a private key. Since we're using symmetric keys in MACs, if I have a symmetric key, you have a symmetric key, we can't prove through cryptography what person actually sent it. If I have my public and private key, you have your public and private key, I encrypt something with my private key, you know that it came specifically from me because I'm the only one who's supposed to have access to that private key. If we're using just symmetric keys, we can't prove what individual sent that message, but we have an idea of what system, what computer sent that message, because the symmetric key would be associated with the computer itself. And that's what we mean data origin or system authentication. A symmetric algorithm will not provide user authentication, but it can provide system authentication. So we're going to look at a couple of examples of using MAC, and that's because I've taught this for so long. I find that people are a little bit confused with how this takes place and what type of security services are provided. So I write you a message, I create a symmetric key, I put both of those values through a hashing algorithm, and what I come up with is a MAC. Now this message is not encrypted. Just because we're using a symmetric key does not mean we have encryption or confidentiality. You could think about just taking a message and a symmetric key, and remember a key is just binary values. It's a random set of values, binary random set of bits. So my system will take my message, and you could think about throwing it in a pot. It'll take the symmetric key, throwing it in the same pot, and then running those values together through a hashing algorithm. And instead of a message digest being the output, it's called MAC. Anytime you see MAC, that means there's a symmetric key involved. Just like with hashing, I'm going to send that message over to you, and I'm going to associate the MAC. So there's going to be a message authentication code value, and there's going to be my message. And you see that the message is not encrypted. Again, just because we're using a symmetric key does not mean that there's encryption here. So I send that message over to you. You're going to take the message I wrote, and you have to have the same symmetric key I use. You have to have an instance of the same symmetric key, which means that you and I have to have an instance of the same key. I'm not going to send you the key. You have to have it. So you take the message, and you take your symmetric key, and you pass it through the same hashing algorithm. And then you come up with your own MAC value. Now if this MAC value matches the MAC value I sent over, then not only do you know that the message has not been modified, so that security services integrity, you also know what system it came from. You don't know that it came from me as an individual, because I should be using my private key if you need to know that. What you know is that it came from a certain computer. That is what system authentication or data origin authentication means. So again, I'm going to put in a block of message. I'm going to write you a message. You see that the algorithm is going to use the key also, and the result is going to be a MAC value, because we have a symmetric key involved. So this is what I went through, what you're going to do. The message is going to go through the same hashing algorithm I created. You're going to come up with your own independent MAC and compare those. Now, when I walk through these steps, most of the time in my class, my students will be like, yeah, you know, you're repetitive, I get these steps. But when I then turn around and ask them, okay, what security services are provided by message authentication code? Those security services are integrity, because we're using a hashing algorithm. There's system authentication, because we're using a symmetric key. Is there confidentiality provided by HMAC? No, because we are not encrypting a message. So again, here's another example of a type of hashing algorithm that you could choose. And we're not doing just hashing. If we have MAC there, MAC, that means we're using a symmetric key also. And the symmetric algorithm is Blowfish. Okay, so we'll just look at this graphic, and we'll just see it's the same thing. If I'm using a symmetric key, what do you have to have? How do you actually reverse the process? You have to have the same message I sent over, you have to have the same hashing algorithm that I'm using, and you have to have the same symmetric key. If you're missing one of those, you can't carry out the reverse of message authentication code and verify that the message came from my system or that there's integrity. Okay, ask these of yourself and see if you understand the answer. Is there encryption with MAC? Message authentication code. Is encryption provided? No, just because there's a symmetric key does not mean that we are encrypting that message. The symmetric key is just a random value that we're adding to the hash algorithm. So there's no confidentiality if we're not encrypting anything. We are not encrypting that message. Is there integrity? Absolutely, there's integrity, because we're using a hashing algorithm. Is there source authentication? What is that? What is source authentication or data origin? That means that you know that the message came from a specific computer, not an individual. So this is the weakest form of authentication. Message authentication code is the weakest form of authentication because we do not have private keys involved. Now there's another type of method, there's another type of MAC that we need to know about. And this is a more confusing approach than HMAC. When you see HMAC, it's just H stands for hashing algorithm, and then MAC means that there's a symmetric key involved. CBC is a mode used with block ciphers for encryption. In block ciphers are symmetric ciphers, so that if you're using a block cipher, one block will go through a encryption algorithm, be encrypted, and then that resulting ciphertext box goes into the next box for encryption purposes. So if we look at this graphic, we have a message. It's cut up into blocks. That's what a block mode cipher will do, and a cipher is an algorithm. So I write you a message. My symmetric algorithm will cut that message into individual blocks. The first block will go through the encryption process, and what comes out of that is ciphertext block 1. The second block of my message is encrypted, but the block from the first process, from the first encryption, is added to the encryption process of the second one. That adds a lot of randomness. So this continues until all of my message has been encrypted, and again what the result is ciphertext. And so what is the MAC, the message authentication code? Just like in HMAC, we've got a symmetric key and the message goes through a hashing algorithm. In CBC MAC, the last block that is created through the CBC method, remember the whole message is cut up into blocks and they're encrypted and the result is the ciphertext. The very last block is what's referred as the CBC MAC. Because we're using a symmetric algorithm does not mean we're encrypting the message. We are using a symmetric algorithm to only create the MAC. So just like HMAC, we're not encrypting the message. The same with CBC MAC, we are not. So when you receive the MAC value, the CBC MAC value in my message, you're going to reverse the process. You're going to take my message, you're going to run it through the same symmetric algorithm. You have to have the same key. You're going to take that very last cipher, you're going to take that very last block that's created after you encrypt the message, and that MAC is your MAC value that you'll compare to mine. Okay, so let's look at an example. I have a message I'm going to send to you. The MAC function here is going through a symmetric algorithm. The last block of the ciphertext from the encryption process of the CBC MAC process is sent over to you. So you see my message of clear text is sent over to your system, and your system has the clear text because it's going to have to take that clear text and put it through the same MAC function. You're going to come up with your own MAC value, compare it to my MAC value. If they're the same, those are the same security services provided by HMAC. HMAC and CBC MAC provide the same security services, which are integrity, because we're using a hashing algorithm, source authentication, because we're using symmetric keys. And you see that the CBC MAC is going on at each place. A CBC MAC value is being created by myself, I'm the sender, and by you, the receiver. So again, this is usually a very confusing concept. You do need to understand how block ciphers work. There's a stream cipher and there's a block cipher. These are both two types of symmetric algorithms. So there's a symmetric algorithm family that does streaming, which is a stream cipher, and then there's a symmetric algorithm family that does block ciphers, which means it takes your message and cuts it up into individual blocks. Those individual blocks are encrypted at one time individually. So we have a message that's cut up into blocks, and you see the first block is actually going to have the initialization vector. We talked about initialization vector in the last presentation. The initialization vector is basically a seeding value. So the first block will use an initialization vector. The actual algorithm will use the initialization vector. There's a symmetric key that's involved for the encryption of that first block. The resulting ciphertext is then used to encrypt the next block. You see that the resulting ciphertext of the first block is used as the initialization vector to encrypt the second block. The second block goes through an algorithm, a symmetric algorithm that uses the ciphertext, and the same symmetric key comes up with the second block of ciphertext. This continues until the whole message is encrypted. The resulting MAC, the very last box, the very last box of the CBC encryption process, is considered the CBC MAC. Okay, so in a CBC MAC, message authentication code, do we have encryption? We do not have encryption of the message. When I send you over my message and the CBC value, the CBC MAC value, my message is not encrypted. Just because we're using a symmetric algorithm does not mean that message is encrypted. So we send you a message that is in clear text, and we send you a MAC value. Because that message is not encrypted, there's no encryption. It's not considered any encryption. It's just that the MAC value is created through a symmetric algorithm process. Is there confidentiality? No. If the message is not encrypted, then there's no confidentiality. Is there integrity? Yes, there's integrity. This is a message authentication code. That's what they're for. Message authentication code is to provide integrity, and a stronger integrity than just hashing, because we have symmetric keys involved. Is there source authentication provided? Yes. If with HMAC and CBC MAC, both ends, the sender and the receiver, have to have the same symmetric key. If you receive a message that has a MAC value, you know it came from a certain system. You don't know that it came from a specific user, because that user would have to use their private key. So MACs are referred to as providing the weakest form of authentication, which is source authentication or data origin authentication. Is there non-repudiation? Remember that non-repudiation means that a sender cannot deny sending a message. With message authentication code, there is no non-repudiation. And that's because if you have a symmetric key and I have an instance of the same symmetric key, I can't deny that I actually sent you a message, since we both have a copy of the same thing. If I encrypt something with my private key, I can't deny it. I can't deny sending you a message if I use my private key, because I'm responsible and I'm the only one who's supposed to have a copy of that private key. So let's move on to digital signatures. So far we've looked at hashing algorithms. We've looked at two message authentication code approaches, which is AMAC, HMAC, and CBC MAC. And now let's look at how digital signatures are created. They're very similar to hashing. I take a message, I put it through a hashing algorithm, one that we've already discussed. I put it through a hashing algorithm, and that message digest value that's created, I encrypt it with my private key. So just like a regular hashing process, I take a message, I put it through a hashing algorithm, I then take that message digest, encrypt it with my private key. Now I send it over to you. I send over the clear text message and the encrypted message digest value. When you encrypt something with your private key, it's referred to as signing, digital signing. So how do you decrypt that message digest value? In public key cryptography, if somebody encrypts something with a private key, it could only be decrypted with the associated public key. So if I encrypt something with my private key, only a person who has my public key can decrypt it. So I write you a message, the resulting message digest value is encrypted with my private key. I send you over the message, and what's associated with that is the digital signature. You take the message, you decrypt the digital signature, you extract the message digest value, and then you compare that message digest value with what I sent over. So when you receive a digital signature, you have to have a copy of my public key. That public key will verify the digital signature itself. Then you know that it came from me. So digital signatures provide integrity because we're using hashing algorithms. They provide authenticity, meaning that you know it came from me because I use the private key, and there's non-repudiation because that means I cannot deny sending a message if I encrypt something with my private key. So here's just an example of some of the configurations a user can do. And we see that the third one is send clear text signed message when sending signed. So send clear text signed message when sending signed messages. Whenever you see signed messages, again, that's digitally signed, which means that a private key was used during the encryption process, and it's not encrypting the message, it's encrypting the resulting message digest value that was created when we ran the message through a hashing algorithm. So again, I said I'm going to be a little bit repetitive because some of these concepts are new to people. So I create a message, I run it through a hashing algorithm. The resulting hash value, or the message digest, is encrypted with my private key. That is a digital signature. I send the data in clear text with the associated digital signature. The receiver will take my public key, extract the message digest value, and then run the same message through the same hashing algorithm and compare the two. If the two message digest values are the same, the receiver knows that the message has not been modified during transmission and knows that it came from me because the private key was used. So what services are provided by digital signatures? Is there encryption? No, there's no encryption of the message itself, which means there's no confidentiality. The only thing that's encrypted is that message digest value. If we do not encrypt the message, it's referred to as not providing confidentiality. Does a digital signature provide integrity? Yes, it provides integrity because we run that message through a hashing algorithm. Is there source authentication? Not really. It's referred to as true authentication. True authentication means that you know it came from a person, not just a computer. Source and data origin authentication is when we have message authentication codes when we're using just a symmetric key. If we're using private key, we know that that private key is associated to an individual, which is referred to as true authenticity. Is there non-repudiation? Absolutely. If I sign something, if I digitally sign something, that means I'm using my private key. Then I cannot deny sending a message. Okay, so we quickly went through some of the complex concepts of confidentiality. We looked at hashing algorithms, how they work, and some examples. We looked at how digital signatures are created and the different security services that are provided by hashing, which is just integrity. Digital signatures provide integrity, true authentication, and non-repudiation. We looked at the two message authentication code types, which is HMAC, which just use hashing and a symmetric key, and CBC-MAC, which uses a symmetric algorithm to carry out block encryption. Okay, so for the next lesson we're going to go through IPsec. Thank you for your time.